Hello Huskies, let's talk about growing number 2. The objective for today is that you can write an explicit equation for an exponential relationship. Now we've already talked a lot about some things very similar to this when we learned about geometric sequences. And in the classwork today we're studying another geometric sequence. We start off with this plan about the king paying the peasants some rubas. And he thinks it's a great idea because, hey, after day 10, he's still only paying 512 rubas, which sounds like a deal, right? If that was pennies, it'd be $5. So you can fill out your table that on the first day, the square 1, you would have 1 ruba. Square 2, you would have 2. Square 3, you're going to have 4. Square 4, you were going to have 8, and so on. They're going to double every time. I just want to add a few things to this table so that we can make sure that we're all understanding exactly what's going on. I'm going to add a line underneath my table called the exponential form. And I'm going to rewrite all of these numbers, the brown numbers for the rubas, using a base of 2 and an exponent. For example, 4 is the same as 2 squared. 2 times 2 is 4. And 8 is 2 times 2 times 2, so that would be 2 to the 3rd power. And 16 is 2 to the 4th. And you could keep going that way. Let's go backwards here. What's just plain 2 then? That's 2 to the 1st power. Now look at these exponents. Start at the right and go left. 4, 3, 2, 1. What is 2 to the something to equal 1? Well, if we just follow these exponents down, 4, 3, 2, 1, then it must be 0. And that, in fact, is true, that 2 to the 0 power equals 1. Anything to the 0 power equals 1. So you can see that although this is like a geometric sequence, what we're learning about today is that you can actually extend this sequence to things that wouldn't make sense for a sequence because we're talking about exponential relationships. For example, what if I add a column in here, and I know we don't have like 0 squares, but how many would be on there? What is the pattern so far coming back? So if you start at the 16, 8, 4, 2, you can see that I'm dividing by 2 or I'm multiplying by 1/2 as we come this way across the sequence. So what would be in this first column would be a 1/2. And just check that. Is 1/2 times 2 equal to 1? Yeah, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, so it works. Well, what if I added one more column over here? Maybe like a -1. I know it doesn't make sense for the chessboard, but for an explicit, for an exponential, what am I saying? Too early in the morning. For an exponential relationship, you can extend this table backwards, and it does actually make sense. So what would be the number that would go here is 1/4. And if I were going to write these using exponential form, it would be 2 to the -1 power and 2 to the -2 power. In other words, that's 1/2 squared. Okay, so we're learning that we already understand a lot about exponential relationships because they are geometric sequences, and so we can write explicit equations. So we've been taught to write an equation that says f of x equals my first term, which was 1, and my pattern, which is 2, and then to say x minus 1 as the exponent. But what is something that is very cool about this is that you can actually use any term you'd like to write this explicit equation. So for example, you could say f of x equals 16 times 2 to the x minus 5. And that's because the fifth term is 16. You see that right here? On the fifth square there was 16. Fifth term 16. Let's do another one. F of x equals, what's an equal sign? Maybe 4 times 2 to the x minus 3. So you could write an explicit equation using any term, and they just have to coordinate. So if I'm talking about the third term, I would use 4 as my starting place. Third term is 4. The pattern is 2 every time on those. Okay, so hopefully that helps you see the answer to the 2 to the 30 question. 2 to the 30, oops, let's draw. If 2 to the 30 is here, which square is that on? Well, notice that the fourth square had 2 to the third, the fifth square had 2 to the fourth, the third square had 2 to the second. So probably the 31st square is going to have 2 to the 30. All right, let's jump right into your homework. We have this story about hours and an experiment and amoebas. And so it says, in the beginning, we had one amoeba. And then every hour after that, we have 4 amoebas. So that one amoeba will split twice, and we'll have 4 amoebas after an hour. Now, each of those 4 amoebas will split twice in an hour, and so we will end up with 16. And so I am multiplying by 4 every time here. And you can keep filling out your table. Let me think what I wanted to do with this here. Oh, you're going to have to be able to write a recursive equation and an explicit equation for the number of amoebas after so many hours. You could, if you wanted to, you could add an exponential row here so that this would be 4 to the first power, 4 to the second power, 4 to the third power, 4 to the fourth power. And so this must be 4 to the 0 power. So you can see that your pattern is multiplying by 4. And you can use any term you would like to start this off as long as it coordinates with this number up here. So you could say that, oh, it wanted us to say t hours. Okay, so then we'll say t minus 3 instead of x minus 3. And it said that we want an equation for the number of amoebas, so we're going to say a equals. So that is an explicit equation, and you can use that as a tool to do the rest. Go ahead and graph it. Okay, on the back, number 2, this is a little bit of review for your sequences quiz, and it's going to just get a little bit outside the box. So what we're saying here is we have this sequence. We went from 100 to 80. How did I get there? At first you might think, oh, I subtracted 20. Well, that's a good guess, but 80 minus 20 is not 64. So this is not an arithmetic sequence. Must be geometric. So then the question is, what am I multiplying by here to give me 80 and from 80 to 64? How do I figure that out? You're going to start to see sequences or exponential relationships that it's a lot harder to see, and you don't know just by staring at it. Oh, look, it's doubling or whatever. So the way to figure that out is if you're going from left to right and multiplying, that must mean that from right to left you would be dividing. And so we're going to use that little trick to work backwards and say, okay, what is 64 divided by 80? And what is 80 divided by 100? If you type both of those into a calculator, you're going to get 0.8 for your answer, which means that going from left to right, I was multiplying by 0.8. And so that is my constant ratio for this. So for number 2 then, not only are you multiplying by 0.8, now you can decide, well, it must have a constant ratio. And I know that it says common ratio on there. That's wrong, but constant ratio, and it's 0.8 because it's geometric. So you're going to circle the ratio. That makes it geometric, and the constant ratio is 0.8. Okay, I hope that makes sense to you. Now down to number 6. You're supposed to write an explicit equation for the nth term of this sequence. Okay, let's find the pattern. Going from -2 to 10, I might be adding 12, but that doesn't work when I go from 10 to -50. So it's not arithmetic, it must be geometric. All right, if I'm multiplying, -2 times what gives me +10? I must be multiplying by -5. And again, if you can't see that, you can go off to the side and do a little bit of working backwards. Negative 50 divided by 10 and 10 divided by negative 2, I get negative 5 both times when I divide those. So I must be multiplying by negative 5. So to write the explicit formula then, let me make a little bit of room here. The explicit equation for this must start at f of x equals negative 2, and then in parentheses I have my negative 5. That's my pattern. Whenever your signs alternate like that, negative, positive, you must be multiplying by a negative number as your pattern. And then we have x minus 1. That is an explicit sequence. You could have put a 10 in the front and x minus 2 as your exponent. That's okay, or a negative 50 and an x minus 3. Doesn't really matter. What I want to know is, can you use that tool you just made to find the 11th term? So we are finding the 11th term, and that's going to be negative 2 times negative 5 to the 11 minus 1 power. Okay, that's going to involve a calculator, and when you type all of that in, you should come up with a very large number, negative 1953125. Let's see. 19 million, negative 19,531,250 is your 11th term on that. So you're just using your calculator. Make sure you type it in correctly and you get the same thing that I got. All right, I want to talk about number 7 because it's asking you to do something a little bit different. If you can find the explicit formula for this, though, you should be fine. So explicit, that's going to start us off with f of x. We know that much, but first we have to decide, is this arithmetic or geometric? Well, to get from 21 to 13, I subtracted 8. 13 to 5, yes, that's subtracted 8 also, and 5 minus 8 is negative 3. So that helps me out a lot. That tells me that my pattern is I'm adding negative 8. And this is arithmetic, so it's going to have no exponents, but it's going to have these parentheses. And so that is a good answer for an explicit equation. If you would like a better answer, you can simplify and distribute your negative 8 and then combine some like terms. So 21 plus 8 is 29. So f of x equals, oh, there's an x there. Oh, goodness. 29 minus 8x. And again, I don't really care if you just come up with the good equation or the better equation, as long as you can use it as a tool to find f of negative 1. So if we're going to find f of negative 1, we're going to take our explicit sequence plus negative 8, and we're going to replace x with negative 1. Negative 1 minus 1 is negative 2. So this is actually 21 plus negative 8 times negative 2. And you cannot add the 21 and the 8 together first. The negative 8, you have to multiply first. Negative 8 times negative 2 is 16, so this becomes 21 plus 16, which is 37. So the negative 1 term is 37. And I know that doesn't make any sense for a geometric sequence, but when we're talking about exponential relationships, it does make sense that we could go backwards and have a negative 1 term or a 0 term or a negative 10 term, something like that. Okay, last one I'm going to do for you is number 10. We are trying to rewrite this using just a base and an exponent. So you have been given 4 choices. It either has to be written as a power of with a base of 2, a base of 3, a base of 4, or a base of 5. So the way I would start this is, what's 125 divided by 2? Oh, that doesn't go in evenly, so it must not be 2. 125 divided by 3? Nope, that doesn't work either. And if 2 didn't work, then 4 definitely doesn't work. But 125 divided by 5 is 25. And 25 is the same as 5 times 5. So what that tells me is that 125 equals 5 times 5 times 5, which is 5 to the third power. And so you can rewrite 125 as 5 to the third power. So just make sure on number 11, 14, and 15 that there are two answers there. You can have 2 and a 4 as the base on those. So give me two answers for 11, 14, and 15. All right, good luck with the rest of your homework and with your quiz that's coming up this week.